This is Vidushi Akshan, William Live from University of Southampton, fourth year students who have just completed their degrees. Last week, I think you got your results?
Yeah.
Okay, so over to you.
Hi everyone, today we're going to talk about the work that our student team carried out as part of our fourth year group design project at University of Southampton in collaboration with Synopsys. So the aim of the project was to verify and implement a RISC-V core using AI and to also assess the efficacy of an AI-driven design optimization tool called DSO.ai. So for this, the project was split into two parts, verification and implementation. For verification, we worked on the Bluespec RISC-V MCU with RTL and UVM test benches provided by Synopsys. And this aimed at giving us hands-on experience with industry standard verification flows. That's something that's not usually covered in university courses. And for implementation, we used Fusion Compiler to implement the same RISC-V core, and then used DSO.ai to get better power performance and area results.
So in order for our project to be considered successful, we were given a project specification to adhere to, which were the targets that we had to meet. For verification, the aim was to learn more about the verification workflow by completing code and functional coverage analysis of a given Bluespec MCU system on chip. Additionally, a save file was also generated for the implementation phase of the project. For implementation, the aim was to assess the efficacy of using AI in time savings and resource utilization savings when trying to improve the power performance and area of the design. For this, we have to create a baseline using Fusion Compiler, which was then input into DSO.ai once the performance and floor plan targets on screen were met.
So now let's move on to verification. I'm going to quickly go over this, and then we're going to go to the main part of implementation. So for verification, we did two types of testing, the brain-up tests, which were done using the existing MCU test bench environment that was given with the design. And for constrained random tests, we used the Google open source RISC-V UVM-based constrained random instruction generator, which allowed us to explore a wider set of instruction scenarios. This helped us develop an understanding of code and functional coverage. And then we also did test grading to carry out coverage analysis. Skip over that. One of the key parts of verification was to generate the switching activity data using the save file. So after evaluating coverage across all tests, we got the highest run coverage and then used it for implementation to guide accurate power estimation and optimization. That's it for verification. Now we'll move on to implementation.
For implementation, the initial steps involve setting up the design. To implement the given RTL as a RISC-V core, we had to input the correct 40nm technology bar, as well as the relevant cell libraries for the SRAM and the different voltage thresholds. Additionally, we also set up multi-corner, multi-mode timing constraints and created a custom floor plan to the specification shown before. Additionally, as part of the stretch target, we inserted the power grid. As seen with the floor plan on the left, we have got a square floor plan with a 70% core utilization. And those are the area of core utilization statistics that we ended up getting. Initially, we had a core offset of 0.45 nanometers. However, we had to increase this to 10 nanometers when we started the power grid, as seen on the right. We had an overall cache size of 1 kilobyte with 16 smaller SRAM blocks distributed around the floor plan. This allowed us to place them more optimally to reduce congestion once the design was routed. And finally, we set up multi-corner, multi-mode timing constraints. For simplicity, we only have one mode, which represented the normal operating mode of the chip. We input the timing constraints within an SDC file, and the timing constraints, such as the clock uncertainty, we monitored the worst negative stack and a forward worst negative stack, which were the metrics for timing, in order to analyze how they would change when the metric values would change. This allowed us to choose the most relevant and realistic values for each metric. Once this was done, we had the finalized baseline, and we input this into DSO.ai for further development.
So for the next step of DSO.ai, we first focused on optimizing each of the metrics for power, performance, and area separately, and then looking at a combination of all these to get optimal solutions. So before going on into how DSO.ai works, it's important to discuss why it was useful in our project. So we know that manual tuning is slow and limited, so optimizing PPM metrics manually requires deep expertise and time-consuming iterations, and that can get complicated, especially with tight project deadlines. Also, the number of flow parameters like cell libraries, tool settings, SDC, among many others. They're too large for exhaustive human exploration, but AI can help navigate this efficiently. Also, AI tools that use reinforcement learning can learn from previous runs and then intelligently select the next set of configurations to try, and this can help improve the design progressively. DSO.ai also runs many flows in parallel, so you can evaluate and compare results faster than human-led sequential flow would allow. Lastly, with objective-driven optimization, we can define customized metrics to guide the AI towards specific design goals to ensure targeted improvements. So as I mentioned earlier, DSO.ai uses reinforcement learning. So each run is like a decision or action taken by the AI. After every run, the tool receives feedback based on power, performance, and area results. And this feedback acts like a reward. So over time, the tool learns what set of parameter combinations tend to perform better and steers the future runs in that direction. This is far more efficient than manually and randomly tuning parameters, hoping for better results. Also, on top of this, DSO.ai can do this optimization in stages. So you can look at the top 5 results from the synthesis stage, use that as the basis for optimization and placement, and then routing, and then so on. And in this way, we can refine the design and explore good design strategies for different stages of the flow.
To guide the AI, we need clear goals for it to optimize for, and this is set by metrics. For example, we may wish to minimize the total power consumption of the design in one session. However, in another session, we might be chasing the highest possible frequency. There are 2 strategies that DSO.ai can use for this. The first one, which is Pareto optimization, balances trade-offs across multiple metrics to find the most balanced solution. In this one, it tries to optimize a metric up until the point where optimizing it further would worsen another one. However, for ADIS, it allows you to assign weights for specific metrics. For example, if you wish to optimize total power consumption over standard cell area, you can do that by assigning a higher weighting for the total power consumption metric, but that still allows you to optimize both at the same time. When used correctly, these 2 strategies help DSO.ai explore the search space more meaningfully and reach optimal results more efficiently. In this example, we use Pareto optimization to balance trade-offs between total power consumption and the most negative stack of the design. In this session, we prioritize total power over the WNS, in that I try to optimize total power first before then optimizing or minimizing the WNS. The green solutions represent Pareto optimal solutions, and these are solutions on the Pareto front. For example, in our design, this meant that you couldn't improve the worst negative stack more without worsening the total power consumption, and vice versa. The run in purple represents the baseline run, and as you can see, the worst negative stack and the total power consumption of that run is displayed. You can note that many of the designs that were found had both a lower total power consumption and a WNS than the baseline one, highlighting the efficacy of DSO.ai when it's used, and Pareto optimization when it's used correctly. In another example, we use ADIS optimization to minimize both the HWNS and the WNS of the design. In this session, we attempted to minimize timing over other metrics such as total power consumption, and this was done by setting a higher weighting for those 2 metrics. The green line represents target metric values for each metric, which were user specified. The blue lines represent the metric values that were achieved by the baseline run, and the red line represents unacceptable values that were set by the user. In this example, you can see that many of the solutions were close to or at the target metric values, which is good news. And most importantly, it had lower values for timing than the baseline run. However, these runs had higher total power consumption, which is undesirable.
So after doing all sorts of experimentation using Pareto and ADIS, we found 2 optimal solutions. One of them, shown by the middle bar on the graphs, was able to run at 500 megahertz of frequency and showed a power reduction of 35% compared to the baseline. It also showed the best congestion and area improvements compared to all the other experiments. This showed a balanced trade-off of all the metrics in the solution. And another experiment was when we did a frequency sweep between 500 megahertz and 5 gigahertz to see how fast we could drive the design till it failed timing. As a result, we found a solution at 1 gigahertz, shown by the rightmost bar in both the graphs. However, increasing the speed meant that power increased greatly by 78%. The next set of slides show the exact numbers, but it's important to note that even though power increased a lot, it was still well under the maximum power limit of 3.38 milliwatts. for the 1 gigahertz solution showed us 0.19 milliwatts of power usage.
When comparing workflows where AI usage is a factor compared to traditional workflows where AI isn't leveraged, we found that in our experience, a smaller team of less skilled engineers can fine-tune performance more effectively. In our group, we needed 5 students to create the optimized baseline, and this was because we had to create a manual floor plan and manually tune the constraints. However, we only needed 3 students to use DSO.ai to achieve the 2 most optimal solutions that we talked about before. Another benefit is that we can achieve competitive outcomes using less resources in a short amount of time. This was evidenced in our project when we required 6 to 7 weeks, including training time, to create the baseline use of Fusion Compiler. However, we only needed 2 weeks to create the 2 most optimal solutions using DSO.ai. This came with the side benefit of freeing up the other 2 students to work on other stretch targets, such as inserting a power grid. It's important to note that AI usage does require more computational resources to run, and that's because it spawns multiple jobs concurrently on different threads. However, in our experience, we found that the time savings recorded made a worthy trade-off.
That brings us to the conclusion of the talk. In summary, we explored different verification and implementation strategies and explored how AI could be used for efficient design outcomes compared to traditional workflow. Thank you so much.
Thank you. You did it in under 11 minutes. Pretty impressive. You brought us back. You saw Mike diving in there. Things. I think we'll reward you. Has anybody got a question? I don't think there's anybody online with any questions. Okay. Mike wants us to reassemble back in the main lecture theatre. So there's a sort of wrap up and some, I don't know, whatever. So thank you to all the people who participated. Thank you in the session. I apologise we ran a little bit late, but we made up the time at the end. So thank you.